Hello everyone, this is Sarah Said, and in this presentation we'll talk about Chapter 56, Corpora and Machine Translation from Corpus Linguistics and International Handbook, Volume 2. So this article concerns the use of corpora in machine translation, and to a lesser extent, the contribution of corpus linguistics to machine translation and vice versa. So in this presentation, we'll start with an introduction on the development of machine translation, and then we'll move to corpus-based tools for translators. Then we'll move to example-based machine translation or EMBT, and then we'll end with statistical machine translation SMT. So first, we'll start with the introduction. So machine translation could be considered the oldest application of computers, and certainly one of the first applications of what later became known as natural language processing. Early history of machine translation is marked at first by fairly ad hoc approaches, using relatively unsophisticated computers available, and with minimal impact of linguistic theory. Then, with the emergence of more formal approaches to linguistics, machine translation adopted what's known as a Chomskyan approach, which entails the use of linguistic rule-based approaches owing a lot to transformational generative grammar. At that time, little reference was made to corpora in the machine translation literature, except in the fairly informal sense of a collection of text, like by researchers at the TAUM group, Traduction Automatique Université de Montréal, who developed their notion of sub-language-based machine translation on the idea that a sub-language might be defined with reference to a corpus, and in the Erutra machine translation project, which was a multilingual parallel text in 9 European languages, which was used as reference corpus to delimit lexical and grammatical coverage of the system. So developers of machine translation systems worked in a largely theory-driven rather than data-driven manner, which is referred to as a rationalist methodology. This methodology has dominated machine translation for several decades, stressing on the importance of basing machine translation development on better theories of natural language. On the other hand, there has been renewed interest recently in more empirical methods, which give priority to the analysis of large corpora of existing translations. And the essential element of corpus-based approaches to machine translation are that they allow systems to be developed automatically, in theory, without the involvement of language experts or native speakers. The machine translation systems are built by programs which learn the translation relationships from pre-existing translated text or apply methods of analogical processing to infer new translations from old. This learning process may be helped by some linguistically aware input that could help in knowing linguistic features characterize the language pair in question. But in essence, the idea is that a machine translation system for a new language pair can be built just on the basis of a sufficient amount of parallel text. Now moving to our second point, corpus-based tools for translators. Since the mid-1980s, parallel text in usually 2 languages have become increasingly available in machine-readable form. The first one of significant size was the English-French-Canadian Hansard. However, this corpus was really just a collection of raw text, and the machine translation methodology had no need in the first instance of any sort of markup or annotation. Some other similar projects followed and became a rich source of data. But with the explosion of the World Wide Web, parallel text soon became easily available, sometimes in several languages and of varying size and quality. Availability of large-scale parallel text gave rise to a number of developments in the machine translation world, and they became useful tools for translators. parallel texts were seen as stores of past translations together with software to access. This led to the emergence of various tools for translators based on parallel texts, such as parallel concordancing, which promised to be a great benefit to translators, and translation memory, which was seen as the one that has had the greatest impact. Both of these applications rely on the parallel text having been aligned. So first, parallel concordancy. The idea is that one can reach for a word or phrase in one language and retrieve examples of its use linked, usually on sentence-by-sentence basis, to their translations. So apart from its use as a kind of lexical lookup, the concordance can also show context, which might help differentiate the usage of alternate translations or near synonyms. Most systems also allow the use of wildcards, but also parallel search, so that the user can retrieve examples of a given source phrase coupled with a target word. This device can be used, among other things, to check for false friend translations. For example, the translation of the Arabic word مكتبة as library rather than bookshop, or to distinguish different word senses. One of the examples of Translators aid is the RALI or Rallies Group's trans type, as illustrated in the slide. This offers translators text completion on the basis of the parallel corpus. With the source text open in one window, the translator starts typing the translation, and on the basis of the first few characters typed, the system tries to predict from the target language side of the corpus what the translator wants to type. This prediction capability is enhanced by maximum entropy, word and phrase-based models of the target language and some techniques from machine learning. An implementation of parallel concordancing is ParaCong as displayed in the slide. This was designed for the purpose of comparative linguistic study of translations. Another implementation specifically aimed at translators is TransSearch, initially using the Canadian Hansard, but now available with other parallel text. It was always thought of as a translation aid. The translation memory is one of the most significant computer-based aids for translators. The idea is that the translator can consult a database of previous translations, usually on a sentence-by-sentence basis, looking for anything similar enough to the current sentence to be translated, and can then use the retrieved example as a model. This brings us to two main issues into discussion: matching and equivalence, suitability of naturally occurring text. So apart from the question of where the data comes from, the main issue for translation memory systems is the problem of matching the text to be translated against the database so as to extract all and only the most useful cases to help and guide the translator. Most current commercial translation memory systems offer a quantitative evaluation of the match in the form of a score, often expressed as a percentage and sometimes called a fuzzy match score. The character string similarity calculation uses the well-established concept of sequence comparison, also known as the string edit distance. In all systems, matching is essentially based on character string similarity, but many systems allow the user to indicate weightings for other factors, such as the source of the example, formatting differences, and even significance of certain words. Particularly important in this respect are strings referred to as placeables, named entities, using the term found in information extraction, or more transparently perhaps, non-translatables. These strings, which remain unchanged in translation, especially alphanumerics and proper nouns, these are the only differences between the sentences to be translated and the matched examples. so translation then can be done automatically. One of the drawbacks with this simplistic string edit distance is that it does not take other factors into account. So let's take a look at the first example, number 1. Given that 1a is our input, the text to be translated, most character-based similarity metrics would choose 1c as the best match since it differs in only 2 words, whereas 1b has 8 additional words. But intuitively, 1b is a better match since it entirely includes the text of 1a. Furthermore, 1b and 1d are more similar than 1a and 1c, so the latter pair may have fewer words, 2 or 6 differences, but the former pair have more words in common, 8 to 4 words. So the distance measure should not count the differences only, but it should also count the similarities. Another example appears in number 2. Considering that 2a is our input sentence, the example 2b differs only in a few characters and would be currently picked up by any translation memory matcher. 2c is superficially quite dissimilar, but it's made up of words which are related to the words in 2a, either as grammatical alternatives or near synonyms. 2d is very similar in meaning to 2a, but quite different in structure. So arguably, any of 2b to 2d should be picked up by a sophisticated translation matching memory system. But it is unlikely that any commercial translation memory system would have this capability. The reason for this is that the matcher uses a quite generic algorithm. If you wanted to make more sophisticated linguistically motivated distinction, the matcher would have to have some language-specific knowledge and would therefore have to be different for different languages. Nearly all translation memory systems work exclusively at the level of sentence matching. So, considering example number 3 as our input sentence and 4a and 4b as our matches, neither matches cover the input sentence sufficiently, but between them they contain the answer. It would clearly be of great help to the translator if the translation memory systems could present partial matches and allow the user to cut and paste fragments from each of the matches. This is being worked on by most of the companies offering translation memory products, and in a simplified form is currently offered by at least one of them. But in practice, it works only in a limited way. Moving to our second main issue in translation memories, suitability of naturally occurring text. There are 2 possible sources of the examples in the translation memory database. Either it could be built up by user, which is called interactive translation, or a naturally occurring parallel text can be aligned and used as a translation memory, and this is called post-translation alignment. The latter method is certainly quicker, though not necessarily straightforward, but has a number of shortcomings since a naturally occurring parallel text will not necessarily function optimally as a translation memory database. So the first problem that we might encounter when dealing with naturally occurring text is that it may contain repetitions, so that a given input sentence may apparently have multiple matches, but they might turn out to be the same. This is, of course, could be turned into a good thing if the software could recognize the same phrase was being constantly translated in the same way. And this also could be a disappointment and plaster any kind of confidence score that the system might calculate for the different matches. A more likely problem that one might encounter with naturally occurring parallel text is its inconsistency. So a given phrase may have multiple translations, either because different translations are appropriate in different contexts, or because the phrase has been translated in different ways, for no reason other than the translators have different ideas or like to introduce variety into their translations. Where different contexts call for different translation, the parallel corpus is of value, assuming that it can show the different contexts. So we have an example here in the translation of the word break in different contexts, from English into Arabic. So when we put it in a context like break the law, it will be translated into يخالف القانون. While when we put it in a sentence like break something, break a vase, for example, it will be translated into يكسر المزهرية. The last example is break record, which will be translated into يحقق. So we have three different translations for the word break based on the context of the word in each sentence.